So,
we got to turn the volume down on that.
Some people wow. No experience.
Too bad.
But when you focus, I was just placing mic check. Maybe Jeremy check.
Mic check. This one probably needs to be turned up a little. It's the lapel mic, upper right. Check 1 2. Check 1 2. Check 1 2. Oh, it's my little clicker. That's fingers on there. Yes, so.
Hello, everyone. Welcome, welcome, welcome on this foggy night. Thanks for coming out, navigating those dark, windy roads. I appreciate it. And you're all welcome. My name's Jan Rush. I'm president of DVAA. I wanted to first give a thanks to Ken Kopplinger, who put together that nice little slideshow that we were watching as you sat down. Give him a hand for that. And for any of you who missed it, such as those of you on YouTube, it'll be posted on the website and you can click on it there. So here we are, January 26, 2024. I want to thank Dan Stern for this beautiful astro image of the Rho Ophiuchi complex. And if you should check out the whole, this is only a part of it because it's a massive image. So check it out on the groups.io site. It's beautiful. So first thing I wanted to mention is a couple of events we have coming up. On February 29th, we're going to have a friends and family night at the Malin Planetarium, which is at the Arcola Middle School in Eagleville. So I think many of you have already been there. It's beautiful, but not only that, it's just been renovated. Brand new software, brand new hardware, brand new dome. They took the whole dome apart and rebuilt that. And best of all, brand new seats. So hope you can all join us for that. It should be fun. And this is on behalf thanks to Adam Chantry, who's a DVA member and the planetarium director. And there's no charge for this. It'll just be DVAA night. You can register for it at the on the website under the events. Just click on the event and there's a way to register. Second thing is that we're starting our winter series of clinics. And this is really we're trying to be something for everyone. So the first one will be February 17th, and that's going to be led by Alan Imperity. It'll start out with a presentation on the different kinds of things you can find in the sky. It's geared for beginners, but it's going to go through all the different objects that you can see, celestial objects. So if you think you'd like to have your knowledge of that topic expanded, by all means come. And then after we do the presentation, he'll also present on the different types of telescopes. So if you're in the market for a telescope, this is a good clinic to come to learn about the different types of telescopes. And then we'll have some set up around the room and you can practice. We'll put some photographs up there on the wall and you can practice using the telescope and get some hands-on experience. So it's really geared for people who are in the market for a telescope or would just like to figure out what it's like to have one. And it's all in the warmth of this room. March 2nd, we're going to have a reprise of a super popular clinic from last year on astrophotography. And this will cover all aspects of astrophotography. I wonder if there's someone who'd like to mention anything about the workshop or the clinic? Anybody? Okay. Here. Sorry, I forgot to prep you for that.
What this first one to cover will all depending on the survey. When you register for this, there's a small survey that asks you what topics you're interested in, whether it's constellations, photography, like skyscapes, or if you're interested in solar system, the moon, the sun, the planets, or if it's if it's deep sky photography of galaxies and nebula. That's all part when you register. There's a little form there. It's just a few questions, like 3 or 4. And if you can put down like at what level you are at. If you've never tried it, if you're only thinking about it, if you've tried it and you want to get better at it, that's very, that would help us out for the clinic, and we can customize it to meet everybody's needs there. But it's going to cover all the aspects from just a fixed tripod right through some deep sky, many hour long photography of galaxies and things like that. So it's a little bit for everybody there. So.
And finally, on March 16th, we're going to have a clinic on Sky Safari, how you can use it in your observing and how to maximize it. Gary, would you like to say anything about that?
So Sky Safari is,
Oh, yeah, need to. Over here.
Uh-huh.
Sky Safari is typically used on a tablet or a phone. And it's basically an astro charting type software, but it also has a lot of other tools in it, like planning. You can make observing lists. You can pan, like zoom to the future, go back and stuff like that. So you can really use that as a planning tool. And as a person who started out with charts and stuff like that, making field of view circles on transparency paper, things like that, all of those tools are built into Sky Safari. And as many of you know who observe that, one of the most important things is knowing what you're expected to see when you look through the eyepiece. How big is your field of view? So we're going to be going through those type of functions, setting it up for actual use in terms of finding targets, searching on them, setting up your field of view, and then cataloging what you found or developing your own observing lists. So it should be, I think, good as a good overview. We're not going to go super deep. There's social media stuff that's part of it. We're not going to go into some of those aspects. I personally do not use those aspects, but like the more useful observing for visual or even for astrophotography kind of tools. Thank you.
Okay, thank you, Gary. All right. So please, if you're interested in any of those clinics, please sign up. The need to sign up here to register at the website. Click on the event and you'll see how to register. And when that happens, you might get asked a few questions or maybe not. Everything's free. This is members only, I should say. This is these clinics are for members only. So it'll be right here in this room, provided the door is open. And I'm kidding, the door will be open. And we hope to see some of you there. Okay, and the last thing I'd like to tell you about is our planned weekends at Cherry Springs. And we now have an S here, it's weekends. So we had reserved March 7th to 10th, knowing that it was going to be a little chilly, but that's a great time to see galaxies, which is nice because you can be out observing and then you could run inside of the lodge and get warm, and it's kind of nice. But we kind of thought people might not be too happy about signing up if you're not a winter person. So we actually, we actually reserved another weekend, May 9th to 12th. So we have room for, I think, about 8 people on this one, and we have room for 15 people on this one. So if you would like to join us for these camping trips, go to the website and sign up. This also is for members only. We're asking one fee to cover all 3 nights. And one of the nights is not going to be good weather-wise. We know that, but we booked 3 nights so that we can go with the weather. We can pick the best night and that kind of thing. And registration is open. Now, here you can see Cherry Springs. There's the astronomy field that we know so well. And here's the Big Dipper Lodge where we're going to have the workshop. You can see it's really close, so it's the same sky. And then there's the Big Dipper Lodge right across the street. It's the Little Dipper Lodge.
You say a workshop? That sounds like we're gonna have work.
Did I say workshop? No.
Yeah,
Oh, I didn't mean
we're gonna get
workshop.
there and you're gonna start handing us tools.
No, not at all. I'm sorry, I misspoke. Yeah, so here you can see the Big Dipper Lodge is here. It's got this big, beautiful field with some low trees to shield it from any lights, from the light of the road. And then if you're bedding down at the Little Dipper Lodge, all you do is you come out there, out the driveway, cross the road, and it's right there. So both places are very close to each other, and we'll do all the observing here. Question? Yes, the accommodation. No, this is no tents. Yeah, good point. Thank you. There are beds, and when you sign up, if you look at the event on the website, you'll see there are bedrooms and there's a dorm style room. So we will match the beds in the rooms with the people who sign up, and everyone will get a bed and couples will get private rooms. So it's pretty nice setup, actually. Okay. All right, now I'd like to ask our chairs to contribute. Brian.
Hi, I'm Brian Lee, the welcoming chair for DVAA. I think we might have a record this month. We have 14 new members. Well, actually, this is kind of a combination. Sorry, it's a brand change.
Okay.
Louis Harris, Simone Spicer, Linda Lindberg, Danny McCauley, John Lucas and Nolan Walton, Martin Knobloch, Brian Ampolsk. I'm not sure about the last name pronunciation of that one. Mike Marino, Kim Small, Joe Ferretti, Finn Tenenhouse, and Paul Broccardi. So, like I said, this might be a record.
Any of them here? Any of you here?
One.
Nice to meet
It's
you.
also written out.
Ah,
Okay.
We won't hold it against them.
anybody here for the first time tonight? Thank you for coming. Welcome. Okay. Now there have been some evolutions, I believe, in the astrophotography workshops that are held every month. Does anyone want to? You want to comment on that, Lou?
I'm Lou, astrophotography chair, and there's a whole bunch of us that are here to help anybody that are interested in astrophotography. We're just getting started, or you're advanced. If you have any questions, we have monthly meetings that we hold the Wednesday that's before this meeting, and you can just click on the calendar for the Zoom link. We're also holding. Well, trying for the first time to have a second meeting during the month, and just look at the calendar for when these are for advanced users that just want help processing. If you need to get a hold of us, if you send an email to astroimagers@dvaa.org, it's on the front page of the club website. It'll go to 7 or 8 of us, and whoever has the best answer will reply. You might get 1 or 2, or everybody might reply if it's a complicated subject. But no one is too inexperienced. We're here to help you get your feet wet, and move you along. We have one member, John. who now is my assistant. Last year didn't know the first thing, and now he's my right-hand man here. So, we really do a lot to help people along. This is something you have to want to do, but we're here to help. Does anybody have any questions? No? Okay.
Thank you. Okay, do any of the other chairs have any announcements? Alrighty then, I hope you've had a chance to buy a ticket. We have an amazing array of auction items over there. If those of you who haven't participated in our auction before, you go over and purchase a ticket and it's how many, what's the cost? What? 3 tickets for $1. At the end of the meeting, we will select a ticket, and if your number is called, you'll get your choice of anything on the table. So if you haven't had a chance to buy a ticket, you can still do it. All right, now I'd like to welcome our program chair, Jeremy, who has an observing talk for us.
All right. Let us stop the sharing. I'm gonna take this off so people can hear me. All right.
This.
No, I don't think I need it. I'll use my outside voice. All right. I actually want to talk about 2 things tonight. So as many of you know, back in the fall, Blue Mountain Vista was sold. So we are in the process of looking for a new observing site. So right now we have a committee. We haven't done too much yet other than getting together a list with some ideas. So I think right now the front runner is Hickory Run, which is up a little bit south of where 476 meets 80. That's maybe about an hour and a half from here, so about the same distance as Blue Mountain. Probably similar in darkness, maybe even a little bit darker. I was hoping to get up there this month, but a couple of a million things happened between work and getting sick and the snow and everything else. So I haven't been able to make it up there, but I think over the spring we'll be scouting out a couple of locations and hopefully we'll find a nice replacement site. Blue Mountain really did check all the boxes as far as an observing site, right? It's dark, wide open view of the sky. You have availability of some facilities. Right? It's a safe observing site. You're not going to get run off by drug dealers and things like that. You're not going to get kicked out by the cops because it's private property and we have permission. Unfortunately, it's going to be kind of hard to check all of those boxes with any one site, but we're going to do the best that we can. So that's basically where we are. I am in the process of writing an article on that, and that'll appear in the February newsletter, which should be coming out sometime, I guess, next week or so. So I'll have a little bit more details and a little bit more about the sort of things that we look for in observing sites. All right, so the other thing I wanted to talk about was winter observing. I didn't prepare any slides for this, but I do have the show and tell, which some of you might remember. So this might be useful, especially if you're planning to go up to Cherry Springs in March, because it can get pretty cold up there. Maybe about 10 or so years ago, I was up at Cherry Springs over Memorial Day weekend, and it got down to, I think, 23 degrees. And nobody was expecting that. We were expecting it to be like 40s, maybe upper 30s at the lowest. Let me tell you, when you don't have enough clothes for the weather, say, in general, if you need it and don't got it, you sing a very different tune. So these are some of the things you might want to have. As far as preparing for winter observing, you want to dress in layers. Layers is going to be king here. We're going to start with good old long underwear.
You won't change in front of us.
No, we're going to save that for the OnlyFans. You got to subscribe if you want to see that. So definitely want to start with layers. Layers is much more important than one big bulky layer. You know, a lot of thin layers underneath, because then you can always put more on. You can always take more off, because you don't want to sweat. You don't want to get too hot. Because then when you start sweating, now you're wet. And then when that gets cold, you're really cold. So start in layers. In fact, usually I know it's about right that when I'm packing up the car, I don't need to have a jacket on. So people will look at you like you're crazy, you know, and it's, 30 degrees out, you're outside with no coat on. But of course, you've got about 3 layers on underneath. You got your long underwear, you got your sweats on, you got your pants on, you got a heavy shirt on. So let's see, where are we going to start? I like to have a nice hooded sweatshirt, something like this. Let's just throw this on. So the nice thing about a hood is it does go up and over your head. Also provides a little shield when you're at the eyepiece. So take that off for now. The hat. There's a rumor about losing 50% of body heat through your head. It's not that high, but it is pretty significant. So you do want to have something on your head. Let's zip this up.
I'm just gonna bake him.
Oh yeah, I'm gonna start sweating in a couple of minutes. Now, one thing I swear by is coveralls, because these will cover your legs too. And actually, I find that when I wear these, my feet don't really get that cold. I think because it keeps your legs warmer, so you have a good blood flow down to your feet. So
2 pairs of socks.
2 pairs of socks, and also get a pair of boots that's maybe a size bigger than you normally wear, because you'll want to have your socks on. Actually, maybe before I put this on, let's talk about some of the ancillary stuff. You can get various hand warmers and foot warmers. So there's these chemical types. In fact, I think there's a couple up there. These are extremely expired. It says 2014, but they still feel good, so they might work. So these are great. You just open them up, you shake them a little bit, put them in your pocket. They get nice and warm. They also make these that'll go on the bottom of your sock. So you put them in there, has a little bit of adhesive on it, like a Scotch tape. Put those in your shoes. They'll keep your feet warm for usually about 4 or 5 hours, but they can vary. Let's see. Gloves. Gloves are important. So here's a couple different types. We got a leather glove. Not going to give you very much thermal protection, but if you're handling eyepieces and stuff, those metal eyepieces. You guys have all seen Christmas Story, right? Touch something metal in the cold, it's extra cold. So that might be good, gives you a little bit of dexterity. There are also things like cut gloves that you could wear. Again, not too much thermal protection, but you get more dexterity. Got your insulate style gloves. I feel like Michael Jackson with the one glove on here. Actually, one thing I kind of like are, these can be seen from space. Shooter's gloves. So your fingers are open, and then if they get cold, seal them away. What else? Oh yeah, going back to hand warmers. So we got the chemical type of hand warmers. There are these old school Zippo type that you put the lighter fluid in. These things get hot. In fact, if this was on, I wouldn't want to be holding this in my hand. This metal gets pretty hot, so it goes in a little baggie. These things will last 12 to 24 hours, depending on how much lighter fluid you put in. These are warm enough. If you're camping out, stick this in the sleeping bag. This will keep you warm. There are also these battery operated ones. These usually don't get super hot. The nice thing about these is they're on demand. You can turn them on and off. I think this one runs about 3 hours, but it could actually last longer than that because you don't leave it on all the time. You can turn it on for a few minutes while you use it. Then if you don't need it, shut it off. And it usually warms up pretty quick within a couple of minutes. You just hold on to it, it warms up your hands. So again, these are the steroid model, right? These will really keep you warm. These are a little bit less, but a little bit easier to deal with. You don't have to pour lighter fluid and all of that. And of course, these are cheap and easy. Throw them in your bag and you have them when you need them. You can always get a hood. Actually, I should put this. Let's not use that with the hat. The advantage to one of these is it will cover the side of your neck. And then you can throw your hood on, maybe the hat too. So this will be good. Now I got to watch out because I'm going to start to sweat. And here comes the main event. So these things, you can buy them. For some reason, they're all designed for people who are about 6'4". I think they're all made for like lumberjacks and loggers. You can.
Well, you want it big, you have all that clothing underneath.
That's true too. Yeah, if you're packed up underneath there, then you can throw this on. I think this is unisex. The best part is you look like Michael Myers when you have one of these on. So if the crazy guy shows up in the middle of the night, you're the crazy guy. So here we go. Pretty hard to beat. All right. So any questions? Yeah, Doug. No. Yeah, COVID masks are really nice, but you don't want to have one on when you're near the eyepiece because you're going to fog it up almost immediately. Yeah, I don't know. There's not really any good solution to that. Hold your breath at the eyepiece. What's that? Is that observing warm weather? Or move to Florida? Get LASIK so you don't need glasses. Yeah. All right. Any other questions?
How hot is it?
I'm starting to sweat. All right. Are we ready for the main event? All right. So a little bit about. All right, a little bit about upcoming programs. Next month, we're going to have Paul Halpern. He's from well, it's now St. Joe's, was with the University of the Sciences, now merged with St. Joe's. So he has a new book out called The Allure of the Multiverse. So he's going to be here to tell us a little bit about that. We're really looking forward to that. Tonight, I'm very happy to have Professor Naoko Kurahashi Neilson. She's an associate professor of physics at Drexel University. She did her PhD at Stanford University. She did her undergrad at UC Berkeley, postdoc at the University of Wisconsin, working with the IceCube group, which does neutrino astronomy. So she's received a number of NSF grants. She's a member of the IceCube collaboration. She's had numerous media appearances, particularly over the summer, because the IceCube collaboration, and you'll discover why it's named IceCube in just a few minutes, recently produced the first image, and I don't want to steal too much of your thunder, produced the first image of the Milky Way. So please join me in welcoming Professor Neilson. So,
Thank you, Jeremy. Okay, I don't think I don't have an outdoor voice, so.
Yes.
This one, you know. Oh, you'll see. I could tell you all about warm weather here. Hold on. Let me just. Thank you. Does that work? No, does that work?
Yeah.
Yeah, okay, great. The beautiful thing is.
how do we have full screen and
Option.
then when you want to show the video, it's
Oh, no. Okay.
so the video is right up here.
All right.
That-
Okay.
it's-
There we go. Yay.
You got your pointer.
Oh, thank you. Yeah, pointer. I'm a very animated speaker, so I'll just see me jump around, but I will try to use the pointer. So I can confirm I am wearing thermal underwear in this picture. Upon many layers, I can confirm thermal underwear is a very good idea in the cold. Okay, so that is me. This is the geographic South Pole. What is the geographic South Pole? So there's the magnetic South Pole. That's where the compass points south, right? And that's over the ocean somewhere. The geographic South Pole is if you have a globe and you know there's sticks there and then the globe spins. Where that bottom stick intersects with the globe, that's the geographic South Pole. So this is the pole in which our Earth revolves around. And that's where I am. So this is on this South Pole is in the middle of the Antarctic continent. As you can imagine, Antarctica has a continent underneath the ice. And I am there. And today I will tell you about why I'm there, why I'm here, and what we discovered. So that's kind of the plan for today. Here are my credentials. So yeah, as Jeremy said, I'm an associate professor of physics at Drexel. I'm part of this collaboration that I'll tell you about, and I am National Science Foundation funded. So those are the people that own me. How do I for it here. Let's see. Does that work? No, does that work? No.
Might not work in the PDF.
Hmm.
Maybe we have to
Maybe if I click on the PDF, it'll work.
make this active.
Okay, yeah. So let me start with a disclaimer. I am, unlike you, not an astronomer. So why am I here, right? I'm here. Well, first of all, what am I? I'm a particle physicist. I'll get to that in a second. So you will all go home knowing what a particle physicist is, what particle physics is, and how it relates to astronomy. That's one of my goals today. But I work with a lot of astronomers. So here's me giving talk at NASA, but I go to like NASA Goddard every other week at this point. So clearly I do astronomy-ish things, right? Okay, and I make maps of the universe. So I'm not quite an astronomer, but astronomer adjacent maybe. So what I call myself, or people like me call ourselves, is that we are particle astrophysicists or astroparticle physicists. Really, we should probably converge on that. So here is who I am, which still doesn't explain why I am here. So these are the three things I want to answer today. Why particle physics? Why am I here? Why the South Pole? Why am I showing you pretty pictures of where the Earth rotates around? And then finally, so do I really do astronomy? And that's where I'm going to head towards in the next 55 minutes, let's say. All right, so humor me for a second. So you're an alien scientist. You're alien. You don't look like what you look like. You're right. And you're a scientist, and your field of study is the human hand. Okay. So this is the only human hand you know of, and from where you are as alien scientists, you need to study this hand. And the only problem is you can't come up and touch it or dissect it or anything. You got to be where you are. How would you study my hand, right? The answer is, not this. Now the answer is that you would look at my hand in different. So you would look at it optically, and you would realize that, well, my hand is like reddish, pinkish, yellowish. There's ridges like this, what I call fingers. But if you took an X-ray image from where you're sitting, you would discover that I have bones inside my hands. If you took an infrared image, if you put on your night goggles, you would realize that my hand is warm. And if you took an MRI image, you would realize that I have muscles inside, so I could probably move it. So what am I trying to say? I'm trying to say that if you want to study something that you can't get to, the best thing you can do is to look at it in different ways. So that is what's known as multi-messenger astronomy. So, multi-wavelength astronomy. So here's the Crab Nebula, and you know what that is better than me probably. Here is the radio image, ultraviolet image, optical image, and X-ray image. This is exactly the same point in the sky. Again, think about my hand, right? It's exactly the same thing. You're looking at the same thing, but in different eyes. And you pick up different features because you're looking at it in different ways. And together, by bringing it all together, you learn the most. So what I want to do, and people like me want to do, is to add particles to this mix, because everything I had in my previous slide, these are all electromagnetic waves, right? It's just different wavelength of light. What I want to do is to add not just light in different wavelengths, but different particles as well, because these stars, galaxies, black holes, they emit not just light at different wavelengths at different energy scales, but they emit particles too that travel to Earth, and we can detect them. So that's why particle physics. Now, I want to tell you about a particle called neutrinos, and this is what I study the universe in. So I actually look at the universe in neutrinos. You may make an image of the sky in your optical telescope. That's in optical light. But I make an image of the sky in neutrinos. So what are neutrinos? They are elementary particles. What does that mean? Okay, so think of a molecule. So everything's made up of a molecule. You, me, chair, everything is made up of molecules. Molecules are made up of atoms. Atoms are made up of electrons and the nucleus. And as far as we know, The electron is not made up of anything. The electron is an electron. No matter how many times we smash it, it does not break into other things. So the electron is a fundamental particle, an elementary particle. The nucleus is made up of the neutrons and the protons. So these are nucleons. And these protons and neutrons are made up of quarks. And as far as we know, quarks are not made up of anything. You can smash them as all we want at very high energies, which is what we do, what my particle physicist counterparts do at CERN, which is a facility in Geneva. You might have heard of it, where the particle accelerator exists. Angels and Demons was a story about this, yeah? Okay. Okay, anyway, that's where they smash these things at very high energies to see if it breaks. Essentially, that's all they're doing. They're seeing what breaks and what doesn't, and what does it break into. As far as we know, quarks don't break, so they're elementary particles. You notice that in none of this, neutrinos came in. So neutrinos are not a particle that make up you, me, air, food, whatever, building, chair. But they are a particle that exists all around us. They are created in radioactivity. So anywhere you think of that's radioactive, there are sites of neutrino production. At lower energies, nuclear power plants create neutrinos. The sun creates neutrinos. And neutrinos are also known as ghost particles because once they're created, they go through everything. So if you think about observing a very dense region in the sky, right? And you want to use light, but at some point it's so dense, the light from behind it doesn't reach it, or the light inside this dense region, let it be a star or a galaxy, doesn't reach you anymore because there's just too much stuff. But if there was neutrino production, it could reach us, and we can see deeper into these sources. So that's the idea. Okay, so that's the particle I'm interested in is a neutrino. That is the one in which I would like to do astronomy with, because when we see the universe in different ways, we get more information out of it. That's the first one. Why particle physics? The second one, why the South Pole? Okay, so if you've ever been buried in snow, or if you've had I don't know why you would do this, if you see a mountain of snow next time and you feel so inclined, stick your head in it, right? And what happens is it gets dark pretty fast. So what if you're buried in a mile deep of snow? Would you see any light from sort of the surface from the sun or somebody's flashlight you? Or would it be pitch black? It'd be pitch black, actually. The photons, the optical photons don't reach you. So it would be very, very dark. And the only thing you'll see is what's known as Cherenkov radiation. And these are high energy elementary particles zipping through. And it's happening here too right now. We just don't see it because it's not dark enough and our eyes don't respond at the right optical wavelength. But it happens all the time. It's just easier to see somewhere dark and dense. So this is kind of the fundamental principle of my experiment, which is known as ice cube. At the South Pole, so if you recall the first image of me standing next to the pole sign, South Pole sign, that's up here. Actually, that is a high altitude location. Even though I'm not on top of a mountain, I'm on top of a very large and very tall glacier. It's actually 2.5 kilometers high, or it's about 1.5 miles, I want to say. So I actually got altitude sick being at the South Pole, which is not the first thing you think about being in. Oh, sorry, I like a lot of interludes. Is it okay if I share stories? So if this is the South Pole marker, and I'm standing right next to it or right on it, every direction you face is north. How do maps work at the South Pole? There is no natural time zone at the South Pole. Right? Yeah. A lot of things happen. That's really mind-bending. We'll get to more things astronomy related too, but so the South Pole is an interesting place, is what I wanted to say. And I'll show you more pictures and things like that. But first, let me tell you why I'm there. So we are there because there is a lot of ice underneath the South Pole. And it has nothing to do with the fact that it's at the pole. This is where we found logistical support to build this. But underneath 1.5 miles of ice, we put in over 5,000 light sensors. They're about yay big. Basically, they're your eyes, but better. Again, you're 1.5 miles deep, so it's pitch black. And these light sensors, 5,000 of them, are scattered on a kilometer by kilometer by kilometer volume. This is why we call it ice cube, because it's a cubic kilometer of ice that we use as a detector, a particle detector. And so every time a high energy elementary particle whizzes by, it emits what I call Cherenkov light, which is the light that it produces, the faint light it produces. These eyeballs catch it for us. The computer, the data gets sent all the way up to this computing warehouse where we have tons and tons of servers that we run. And this is how we try to catch particles. The high energy particles that I want to catch are very rare. So it has to be a big detector. And this is why we have a cubic kilometer of ice. So there was not a lot of places in the world where we can access a cubic kilometer of clean ice, right? Clear ice, clear, clean ice that had logistical support to build an experiment like this. And one of the places happened to be the South Pole. Yeah.
How did you get down 1 mile deep?
We invented something called a hot water drill. So you just literally melt. The hot water spewing out and you melt. And the drill is heavy and you dangle it. So it's gravity, like you just hope and pray you're going straight down. Now, I don't know, this is kind of a mind-boggling slide because I always tell people, like, if you ask me to run 2.5K that way or 1.5 miles that way, I probably can't run that far. That's really far and I'm really out of shape. But they did that this way, right? They dug that way. So it's like an amazing engineering feat. Here is one of those holes that we dug. As soon as the 1.5 miles is cleared, we lower these light sensors on a string. Fun fact, this hole that is, again, 1.5 miles deep, just over your shoulder width, big. So you don't want to stand too close to it. Yeah.
And how many holes?
We drilled 86 at Bend. I'll get to the other fun fact about constructing a cell pole. Yeah. Yeah. Yes. So any nuclear processes would produce a neutrino. Really, the technical thing, if you understand technical jargon of radiation, is beta decay. Anything associated with beta decay, anything that has to do with the nucleus going through some reaction, fission, fusion, that produces neutrinos. And so where I'm going back to really is that you can imagine a lot of stars and particularly supermassive black holes. They have all these processes, nuclear processes that happen, and the byproducts of that are neutrinos. So we should have a lot of neutrinos produced at these sources. Yeah. That tough crowd. I was not prepared to go this deep into particle physics. I love it. Okay. Because I do a lot of outreach talk. And usually this is the part that gets glossed over. So okay, you guys, I really appreciate this because this is my so the neutrinos, there goes particles, they go through it. So if I had like a neutrino flashlight, which I don't have, I wish I had, right? A normal flashlight, if I try to flash it through this thing, you won't see the light on the other side, right? But if I had a neutrino flashlight, again, which is not invented yet, you would see the neutrinos streaming out, no problem. So it goes through a lot of things. In particle physics, this is called a weakly interaction thing or a long interaction length or a small cross section. All of those things are kind of related. And what that means is that it rarely interacts, but once in a while it does. And when it does, it goes through something called the weak process, which is a radiation term, a particle physics term. But it interacts normally in our detector, because we're looking for very energetic neutrinos, and interacts with the nucleus of the water molecule. And it actually goes deep into the nucleus and breaks it entirely apart. Yeah, it fragments the nucleus. It's so energetic. and the result of that is all the Cherenkov light, and that's what we detect with our eyeballs. Yeah. Yes. Yeah. Mm-hmm. Yeah, that's a great question. So the light production is, yes, it's part of stopping the really high energy particles. So as it gives off light, it gives off the energy, and eventually these very high energy particles stop. You're correct. However, even though we have, sorry, let me try to get to where so even though we have a kilometer of ice, these neutrinos are so energetic, the neutrinos that the black holes produce are so energetic that they don't stop. So we see them traversing the entire kilometer. Correct, yes. And normally, like neutrinos produced in the sun or nuclear reactors, they would not traverse the entire length. They will give off energy and stop.
Same type of experimental clean fluid.
Yes, this is the solar neutrino problem. Oh, you know this. Okay. So the way neutrinos were detected, or so first discovered as a particle, has a lot to do with astronomy, because the first source of neutrinos that were ever detected was the sun. And wait, is that true? No, sorry, neutrino oscillation was the sun, not neutrinos. Neutrinos were from double beta decay or beta decay. The first source of the neutrino problem, there in the 70s, 80s, possibly up to the 90s. People were not pretty convinced yet. In the early 90s, there was a conundrum because neutrinos from the sun were missing. So we knew enough about neutrinos, and we knew enough about what happened in the sun in terms of nuclear processes, and we could kind of figure out how many neutrinos we should be detecting at. But we weren't detecting enough of them, and that was known as the neutrino problem. So it turns out neutrinos change flavor as they fly from the sun to us. And that's kind of a technical, even though flavor is like a jargon term, it's a technical term to say that the neutrinos change type. So if you're only detecting one type of neutrino and they change into another, then you wouldn't be detecting it. And that's how the number of neutrinos were missing. And if you go through the math, which I will not, the fact that they can change types in flight implies that neutrinos are not massless. Not massless, so they are massive, so they have mass. So they have very minuscule mass. This is one of the fundamental differences between neutrinos and photons, or light, is that neutrinos have a tiny bit of mass. This is very technical questions. If you understood none of that, audience members who have not asked questions, do not fret. You can still understand the rest of the song. Do they have a quantum field? What do you think, Jeremy?
They interact with the
Weakly, yeah. So they, and gravitationally, obviously, because they have mass. And negligibly, yes. Let's say that's the political correct. Okay, so here's an artist's, view of, here's our light sensors, clearly they did not draw 5,000 of them, but here's the light emitting particle traversing through. That's kind of the image of what happens. So such a big experiment cannot happen with me alone, obviously. So we're a big international collaboration, the IceCube collaboration. We have about, I think, close to 300 scientists from, I think it was 15 countries and 50 institutions around the world. I am the leader at Drexel, but we have a lot more institutions in the United States. And so this has been a fun experiment, basically, because you got to know international colleagues very well. Okay, which one am I pressing? Here. I'm sneakingly included, because usually it's not about particle physics, it's about the South Pole. So I sneakingly included a show and tell about the South Pole. How do you get to the South Pole? So if you look at a map, Antarctica is like this long thing on the bottom, but obviously it's not a long thing on the bottom because that's a projection issue, right? Maps, flat, Earth, not flat. So if you look at a globe like this is what you see. This is the outline of the continent of Antarctica, and the South Pole is right here in the middle, obviously. So how do I get to the South Pole? I fly commercially to Christchurch, New Zealand, which is here. Christchurch is on the southern island. And then from there, I exit the Christchurch airport and go to one building over to the United States Antarctic Program, or USAP, passenger terminal. This is where all the United States Antarctic stuff is run from. There you're issued your gear. So you'll see in many photos, we're all wearing the same parka because they're lended to you in Christchurch. So if you show up in flip flops and a tank top, they give you enough stuff to not die. And the gear is actually very good, very high quality gear. You have to return all of them when you come back through Christchurch. Thermal underwear also provided. Also, you have to return them. Very high quality things though.
So it's all been used before then.
Obviously, yeah. Nothing is new, no. Here are some of the international bases in Antarctica. So the South Pole Station is called the Munson Scott South Pole Station. If you are interested in any history and have not done so yet, the journey, the race to the South Pole is an amazing story between Amundsen, who's from Norway, and Scott, who is British, a British naval officer. They chronicled everything. It's an amazing story. When I was there 12 years ago, 13 years ago, so was the centennial anniversary of these two men reaching the South Pole. Spoiler, one camp dies on the way home, and it was not the winning camp that got there first. And his diaries are written in English and amazing. So I read it as tradition in my collaboration. Before you go to the South Pole for the first time, you read the Scott diaries, and it's a lot. Like, it made you want to die for Queen and country. So yeah, light reading there. Anyway, nowadays there's a lot of bases operating at the South Pole, or sorry, in Antarctica. You can see most of these are coastal, right? They're all coastal stations except for the South Pole. The largest base in Antarctica is McMurdo. This is the coastal US base. So the first thing we do, or I did, was fly from New Zealand to McMurdo. So back then, this has changed quite a bit actually, but nowadays we don't have as many scientists going to the South Pole, but or Antarctica for that matter. But back then we used to fly in these Air Force cargo planes. That's me inside. That's all of us coming out of the plane. Happy to be on Antarctica for the first time. This is Ivan the Terrabus. It picks you up at Pegasus Field. This is the airfield in McMurdo. So they actually do their airfield on the stable ice next to the base. So it's not right next to the base, but it's actually a little ways away. And here's the bus that takes you from the airfield to the actual base. You can see some smaller airplanes back here, maybe. Maybe the resolution is not so great. You can see that this plane landed on wheels, but landed on ice. Yeah.
And how cold was it?
It's not that cold, especially in the summer when I went. I mean, it's like probably like coastal Alaska in the winter, like not that far north coastal Alaska. So I think, it's below freezing, but not much. Yeah, I don't remember the temperature all that much. So, because this is a transit point. So here's, I hiked up this hill called Observation Hill, or Ob Hill. This is the entirety of the base that you can look down on. In summer, the population gets to about a couple hundred to 500 maybe. So it actually gets pretty crowded. I don't know if that's still true. Back then it was true. You can see a lot of wildlife at McMurdo Station because it's coastal, it's temperate. I don't know, sorry. Words are starting to escape me. But it's cold, but not that cold is the point here. But we will get colder. And by we will get colder, I mean we'll go to the south. So from McMurdo, we hop on this plane, which is a different kind of cargo plane. You can see, maybe you can see it better in the next picture. This plane takes off from McMurdo Station on wheels, lands at South Pole Station on skis. So at South Pole Station, there's no ice, so it's a skiway, not a runway. Here are the pilots, obviously not paying attention to flying over the Transantarctic Mountains. It's beautiful. Here's me in the plane. So this thing is the toilet. Back here is the pilots. And from here, looking back, because it's a cargo plane, it looks like that. Not a lot of people go to the South Pole. The South Pole, this flight, so the flight from Christchurch to McMurdo on those C-17s are about, I recall 5 hours, I think maybe a little bit more, 6 hours. Because there are no alternative airports, there is a point of no return where once you pass that, you are committed to land in Antarctica, right? So what that means is that if there's any doubt that you can't land in Antarctica, you turn around while you have fuel. This is called boomeranging. And so depending on how unlucky you are, people can boomerang for like 10, 20 consecutive flights every day because it's just so weather dependent. Same thing happens here. So I boomeranged a couple times trying to go to South Pole, I think. Again, there's no alternative airports. So you are committed to, landing at South Pole Station skiway. There's no other airport you can divert to. So if you don't think you'll make it for any reason, you go back to McMurdo, and this happens quite a bit as well. Okay, here I am landing at South Pole Station. Maybe you can make out the skis just about. This is the skiway. It's flat, it's white, it's deserted. The running joke is it's like Southern Illinois in the winter. Yes.
So where do you get your energy from? Is there like?
Yeah.
Power plant?
Yeah. So there is a power generator. These planes actually fly with full fuel and they unload at the station. Yeah. So we fly heavy. A lot of the cargo is fuel, actually. Most of the cargo planes' cargo capacity in terms of weight is taken up by fuel.
So what happens when you run out?
You can't. I'll get to a more dire situation. I'll tell you about winters soon, and you really can't. Fun fact about fuel. So they can't use gasoline because it's too cold there. So everything uses jet fuel. So even you'll see like me on a ski scooter thingy that operates in jet fuel. Every vehicle operates in jet fuel here. Yeah, that's me, that same picture again. That's another view. And here it's very different from McMurdo. It's high altitude, but it's significantly colder. There is no naturally living thing at the South Pole, not even bacteria. So whatever living thing there is currently, we brought it in, but it doesn't survive outside the station. So it's contained in the station. Yeah, I think that's what I want to say right now. Oh, okay, video. Let's see, Jeremy, you think I can do it? Where is my mouse?
Oh, it's upper screen.
Oh, sorry. Idea. There's a video of me at the South Pole that's kind of fun that I like to show sometimes when the audience is right. Me being a little bit happy there that I ran around the world. Exactly. So on New Year's Day at the base, there's a race around the world that's a little bit longer than that. It's like a marathon. Okay. So I don't know if you've heard the crunchy ice snow sound. If you're from somewhere really cold, like people from Minnesota understand right away what that snow sound means. It means it's really cold. Okay. That's me. Okay. What happens in the winter, right? So I visited the South Pole in the summer. I flew in, 6 weeks later, I flew out. In the winter, it is too cold for planes to land at South Pole Station. So we leave about 30 people behind. We say, see you in 5 months. We can't come help you if anything shall happen. And these brave people have volunteered to do this. This is the last plane leaving the South Pole. So up until now, all the pictures are from me. From here on out, my friend who's wintered over, I think about 7 years ago, sent them to me. So there they are, waiting the last plane of the season. They will not see another new person for 4.5 months, 5 months, depending on weather. It's crazy, crazy. Yeah, so Austral winter, where the base closest, is like, I think March to November. Would that be, that's 8 months. No, maybe it's a little bit, maybe they could go October sometimes. So somewhere around there. Yeah.
How do they communicate down there? Is there internet, satellite?
I will get there, but if I maybe I didn't put that in. Maybe I'll just answer you. There is no geosynchronous orbit at the South Pole. If you don't know what that means that if you were in Earth, right? And you live here in Philadelphia and you're going around the Earth like this, right? So you launch a satellite and then the satellite, as the Earth rotates, it rotates with it, right? Oh, Jesus. This is what happens when I give presentations. I'm just dancing. Yeah, that's a geosynchronous orbit. What happens if you're at the pole, right? Your horizon, in terms of space, is if something is on the equator, you never see it, right? That's from the South Pole. So you can't have a geosynchronous orbit at the South Pole. So there's a couple of these constellation satellites that orbit like not geosynchronously. And so once in a while, a satellite comes up. There's actually a screen in the mess hall that tells you exactly from what minute to what minute we will have internet today. Yeah, and when that clock hits that time, everybody goes back to their room and updates Facebook or whatever we do. And then the satellite goes down and all of that. For emergency purposes, we have an Iridium link, which is another satellite system that's many more based off the Iridium, atom, yeah. So there's, that is, one thing is always up, but the bandwidth, communication bandwidth for that is small. So it's reserved for low throughput sort of communication, like over the phones, things like that. There's no sending data out.
What about Starlink?
That wasn't up when I went. I don't know if you can see it from the South Pole. Does it have an orbit? That it's
I thought they're all in low Earth orbits and they were sun
like,
synchronous.
oh, really?
I thought so. Or high.
So the satellites that do come up and down, we share that bandwidth with the International Space Station, I know. And some other gamma ray experiments that are space-based. So that's what we do. How long is a typical window of internet connection?
Yeah.
Like it could vary from like 20 minutes to like 2 hours. Oh yeah, yeah. Oh yeah. Oh yeah. All the Facebook posts, all the emails, all the blog updates. Yeah, you have it all set. That's what happened. Okay. So I don't know if you know this, but at the South Pole, there's only one day a year, right? Summer is daylight time and winter is nighttime. So what happens in between? You guys are astronomers. What happens to the sun in between? Must set. How does the sun set at the South Pole? Yeah, that's right. That's right, Jeremy. That's right. That's right. Yes. So in the fall, the sun gets low. The sun does this basically every day, right? It just does that on the sky. And the fall, it gets lower and lower every day. Starts setting, and you have about 2-3 weeks of sunset where the sun just is on the horizon doing this. And every day it goes a little bit lower and a little bit lower. And then the sun sets for the year. So here's like a trace of the sun, I suppose. Yeah. Okay. I guess that was my show and tell. I thought I had more pictures, but I guess I didn't. You could ask me anything. I'm happy to chat about everything, obviously. That's why I'm here. So yeah, a few jokes about the South Pole. We say that, you know, there's a psych test, psychology test to winter over. We say that that's to make sure that you're already crazy. All right. Sense of humor of winter overs. Once the base closes and they say bye to the last plane, their tradition is to go to the media room and watch The Thing. I don't know if you know this movie. Yeah, some of you know what I'm talking about. The Thing. Great movie. You should see it. Long live the 80s. For those who don't know, it's about a remote Antarctic base where the alien takes over one human at a time, and it's a remote enough base that you only just I forget, it was like 7 of them in that situation. And you don't know which one's an alien and which one's a person still. So anyway, that is the kind of humor you need to have to winter over. I would never. Okay, yeah.
I'm curious about the week of sunset.
Yeah.
And the cloud cover and.
Yeah.
What about the winds in that?
Yeah, so the winds, it's funny, right? Because there's not much precipitation at the South Pole. It's very dry. I guess it's like a high dry desert, if you will, but it's not a desert, but, you know. So most of the snow accumulation is from drifting by the wind. The weather pattern in the South Pole, it has, the wind definitely has like a, I think it was counterclockwise. Anyway, it's a circular motion wind. So if you launch balloons, like some of my friends do balloon experiments, high altitude balloon experiments, for NASA in Antarctica, and they always launch and they want to, they're, you know, that's only propelled by wind. So you want to like, how many circles can you complete is kind of the topic that they discuss. So there's a circular motion wind around Antarctica. What happens at the South Pole? I don't know, actually. I don't know if there's like a definitive weather pattern there or not. Certainly there were cloudy days and sunny days and windy days and not windy days. And if you go outside on a cloudy, windy day, it feels so much colder than on a sunny, still day. Yeah, I learned that the hard way. Yeah.
So if you plan a stick in the geographic itself.
And
It moves because the ice moves.
yes, this gentleman knows what it's like. So every year we have to replant the South Pole stick. Because the Antarctica is a continent and there's a huge ice sheet on it, as I've told you, it's a kilometer and a half. Or sorry, a mile and a half high. It is slowly falling off into the ocean. So every year, everything moves by, I want to say about like 10 meters. Or maybe a little less, so maybe from here to that door. So every year they pick up the stick. They actually don't replant it. They have a competition because there's a lot of good machinists on site. They have a competition for the new stick of the year, the new South Pole marker of the year. So everybody enters their like really intricate metal work. And then they vote. And then whoever's the winner, the new, you know, that 2024 South Pole marker gets planted in the new site. So everything is moving a little bit at a time. Yeah.
And what's the record?
Geez, I don't know.
North.
North, yeah. They'll be here all day, folks. Yeah. No, that's a good one. Sorry, I should have caught that. Very good. That's right. I mean, it's kind of in the middle. Everything is a little spread out and it's kind of in the middle. So it's a very, it'll take decades, if not centuries, for it to really be out of range. And a lot of the experiments that happen at the South Pole use a wide footprint. And even aside from ice cube being like, you know, it has a square kilometer footprint, obviously on the surface, but there's other telescope experiments, but also there is what's known as the clean air sector. So this is where they've been measuring greenhouse gases since like something like the 50s or the 60s. Every day they launch a little balloon. They measure the I don't know what they measure, the aerosols in the air, I guess. This is how much I know about other fields, right? And then they record it, and they've been doing that every day for the last 80 years, maybe 70. And that is the best data we have of greenhouse gases in the world because it's a clean air sector. There's no activity. There's no, you know, local activity to mess with the measurements. Yeah. Yeah. It's all ice shift. So yeah, to first order. Continent doesn't move, I think. Yeah.
Couple inches per year.
Maybe. I mean, I don't know. I'm not a geologist. Say again, I'm sorry. Does that affect the pole location? I don't know.
From with
Yeah, so it's a pivot. The pole is the pivot. Yeah.
Yeah.
Okay, yeah. Yeah, I never thought about that before. Yes. I would like
the nutation happens over 6,000. Not quite.
long live us to see that, I guess. Getting there. You want. So do you do astronomy? So once the sun sets, this is what you see. I like this picture because it preps me up for the next thing I want to talk about, which Jeremy already told you about. So I like this picture for two reasons. You can see two things. First, the aurora australis, or the southern lights. This is this green light. Oh, by the way, the foreground, this building is our computing house. So all of our sensors are under the ice. The cables come up here, through here, and feed into computers. It's really, really mechanical. So that's a two-story building. Because of snowdrift, it sits like high like that so that it doesn't get buried, basically, the building. Okay, back to what you see in the sky, because this is an astronomy talk after all. You see the southern lights, and then you see, of course, the Milky Way. So let's talk about that. The Milky Way. This is an iconic image of the Milky Way. And before I tell you about that, which I think most of you might know, but just in case, iconic image, because here's my student's office, my PhD student's office. And of course, next to the periodic table, you have one version of this poster, which NASA produced every year for like many, many years. So when I give talks at any NASA locations, there is always somebody in the audience who can tell me which year this poster was produced based on the data available on the poster. So what are we seeing on the poster here? What is this image, right? So this is something I need to do because I'm not an astronomer. So for non-astronomy crowds, this is important. This is our galaxy. This is our Milky Way. Here's the center of our galaxy. There's a bar. We are a spiral galaxy, and we live around here, where the sun is here. It is a flat galaxy with a bulge in the center, so it's like a pancake. And if you live on the outer edge inside the batter of the pancake, and you look towards the middle, what do you see? You see the cross-section of that pancake. So if you cut the pancake like that, that's what you see here. That's the bulge, that's the galactic center, and that's kind of the disk. So again, edge-on view of our galaxy becomes that in the sky. Now, let's straighten that out and put the galactic center at the center, and that's your galactic coordinates. So this is an image of our Milky Way in galactic coordinates. So let's go back to this. So that image was, where's my optical image? This one. Remember earlier we talked about multi-wavelength astronomy, how you want to see the stuff in the sky in different wavelengths. So this is the same image of our own galaxy in radio. This is what it looks like, emitting in radio waves. Our own Milky Way emits a lot of radio waves. And you can go from radio waves, don't quote me on this, I think this is infrared, maybe high frequency radio, I don't know. And then you go to optical, and then you go to X-ray, and then you go to gamma ray. X-ray, and sorry, this is optical, I'm sorry. You can tell I'm not an astronomer. X-ray, and then gamma ray. So this is, again, the same, this is all light, but the wavelength getting shorter as you go down, or the photons getting higher energy, if you want to think about it that way, or the frequency getting from low to high, if you want to think about it that way. Same image of our galaxy. Okay, and what we did last year is we presented for the first time, we discovered the same image in neutrinos from the ice cube data. This blurry image is our first view of the galaxy in something other than light. So remember I said I want to see the sky in particles. This is the first time we see our own galaxy in particles, in any particles other than light. And that's what we discovered. So we had a press conference at Drexel where I work. You like the banner, we're very serious. We dressed up. We don't normally look like this when we work. There's me giving a talk. If you are so inclined, this is the Science magazine paper. But I don't recommend reading that. I recommend reading the New York Times article on it. They did a really good write-up. And not because I'm quoted like 15 times. So if you Google New York Times, neutrinos, Milky Way, you will get this. This is the first hit. And you can read all about it. And this photograph might look familiar to you. And you can tell your friends all about it now. When-
the date?
You should know because it's the date of the press conference, June 2023 sometime. Yeah, there will only be one neutrino Milky Way article in the New York Times, unfortunately, yes. My friend's kids have a subscription to like a Scientific America Kids version that had a very big feature of this, basically this article in kid-friendly format. So if you have kids in your life that you want to show, I think it was the kids version of Scientific America. And then, yeah, we did a lot of press. I'm quoted everywhere. Even the Inquirer had like a picture of me and my graduate student on the local section. So we were all over the media that day, but I recommend this article most because I think the science writer, he did a very good job writing this up. Okay, so this is about that observation. I was gonna stop here because I assumed I'll run out of time and it gets way too technical, but you guys apparently like way too technical, so maybe I'll answer your question a little bit.
Can you tell Don?
Yeah. So this image is about, I want to say like 50,000 neutrinos collected. So it's clearly not just a density map of where they come from. The other problem here is that the neutrinos we use for this discovery, and this was kind of my idea and invention, for various technical particle physics, we couldn't use the very sharp image ones to look at our own galaxy, mostly because the reason is that our galactic center is in the southern sky. So what we used was what we used to think were low quality neutrinos, where the localization in the sky was bad. So if you have you're astronomers, if you have a photon coming, right, you can localize it there, like your eye says, it came from there, plus minus this much, like this is my error circle, right, very small. These neutrinos, I can tell you, it came from there, plus minus this error circle in the sky. So it's a huge error circle in the sky. And it's only because we collected over 30,000 of them, now I'm not sure about the exact number, that we have any image recognizable as the Milky Way. Now the contours here is, these contours are based on some models, based on actually gamma ray observation of our Milky Way. This is where we think, I think it was 90% and 60% of neutrinos should come from. So 90% of the neutrinos should come within this error circle and 60% should come from within this dotted error circle. So that's kind of the contour of where you expect most events based on a model that we were testing. Yeah. What other technical things would you like to know? Yeah. Red sweater.
Your ice cube sensor.
Yeah.
How many sensors might register one neutrino?
Yeah, so for this analysis, that's a really great question. For this analysis, I think the average is about, I want to say like 100 to 300. Yeah.
So the more sensors, the more accurate.
That's right, yes, and also higher energy, actually. So the higher the energy, the neutrino, the more light it emits, and more sensors see it. And there's we actually used a lot of machine learning to figure this out, like how to use that data of the many hundred sensors in order to localize it in the sky and things like that. And then 1, 2, 3, let's do. Yeah.
So Ice Cube is this incredible thing. Assuming it's the state of the art observatory in the world right now.
Correct.
But where does it fit?
Yeah.
Is it at 10% better than the last one? Are you looking to expand it to
Yeah.
make it 10 times better? What's the deal?
Yeah, so as of now, as of like today, it is kind of the one and only. Until last year, there was a competitor experiment actually in the Mediterranean Sea. So parts of the Mediterranean Sea are very deep, and if you go that deep, same thing, it's pitch black, except for when Cherenkov radiation happens. So they actually made a tower of these light sensors in the bottom of the deepest part of the Mediterranean Ocean. This is our European colleagues. The telescope's name was called Antares, and they were much smaller than Ice Cube, but they operated for a long time and had some results. And I think I'm okay in saying this, like they were maybe like, I want to say like maybe like order of magnitude lower in sensitivity. So, if we were 100, they were 10, kind of.
Yeah.
Now, they turned that off last year. They are now making something called KM3net, so cubic kilometer network, which is their new successor to Antares. They're in the building phase still because again, building something like this takes enormous effort in many, many years. So they're still in the building phase. They're not yet bigger than Antares, the thing that their predecessor. So, but they are trying to expand on that. There are other efforts in Lake Baikal in Russia that's been going on for a very long time. Again, much smaller than Antares. And then there are new plans to do it. I'm involved in a new plan to do it in the Pacific Ocean off the coast of Canada and Vancouver Island, actually, or Victoria Island, I'm sorry. And that one we'll see. We are still like in the very early days of deploying things. And then there's a enormous effort to do it in China. And am I allowed to say this on Zoom? Is this going to get posted on YouTube? I won't say it.
Yeah. So just these are also, when you're saying large, these are of the type, basically the.
Yeah, same kind of.
Because there are other types that like a big mine has detectors and.
Yeah, so those neutrino experiments you're thinking of are definitely neutrino experiments, but of a very different type.
Yes.
So they're looking at the 10 to the 6 times lower in energy, so a millionth of an energy of what we look at. And so it's not for the purposes of astronomy per se, it's more for the purposes of the neutrinos, the properties of the neutrinos, sometimes using the sun still. So they don't really make sky maps like we do. They make maps of the sun or the images of the sun, but not of the sky. We were going to go there. Yeah, that's a great question. Back when we started drilling, or even before that, we found that the logistics all supported itself was better.
Guess I can't see the galactic center from Greenland.
We didn't know that at the time. What do I want to say about this?
I need an astronomer.
I need the YouTube. There are geopolitical reasons for many countries to be in many places, and I will stop. There was another one over here.
Can you sort of outline the varieties? There
Yeah, so yes. So very good question. Something I skipped over entirely is that what our detector sees mostly is not neutrinos. We see cosmic ray muons, atmospheric muons. And what are these things? So our atmosphere on Earth is bombarded by cosmic rays, and they produce a particle shower in the atmosphere. And there's different kinds of particles that get made, but the one thing that gets made that lives for a long time are muons. So these are, again, a fundamental particle, again, not observable by smashing our atom and breaking it apart, but it is something that, like a neutrino, but heavier, that gets produced in the shower of particles in the atmosphere. And then these cosmic ray muons, cosmic ray produced atmospheric muons, they're problematic because they live for a long time, so they can penetrate our atmosphere all the way to the surface, and then penetrate the ice for a mile and a half and actually reach our detector. And so, because of how the particle physics works out, these particles don't lose a lot of energy as they travel. I think that's the best way to put it. So they, our trigger, our detector is triggered. Then comes atmospheric neutrinos. So this is getting really technical. I have slides for this. I just didn't think this was appropriate for the audience, but now we can get it wrong. In the atmosphere, the other thing that gets produced are actually neutrinos. So these are called atmospheric neutrinos. These are our backgrounds as well. They actually hinder our ability to see the stars and the galaxies behind it. So these are our foreground, if you will. So how I like to say it is that basically it's like trying to do astronomy in downtown Los Angeles with all the light pollution around, right? So things we want to see are behind the larger things that get produced in the atmosphere, the local particles, and we have to see behind it. And we have to be very clever about how we do our data analysis in order to do this. So the biggest challenge, and I don't know if you've heard like big data science, we are really big data science detector because we trigger at 3 kilohertz. So that means at 3,000 times a second, as I speak, the detector at the South Pole is recording a particles. So we've been on for over 10 years, and we're never on. 10 years, every second we have recorded 3,000 particles. That's a lot of data. Almost all of those are not neutrinos. So we have to filter this. So again, it is not, it's like doing, astronomy in the glaring light right next to, whatever, whichever downtime you think is the brightest. So that's why it's tough. The business is tough, and it's not as easy as turn on telescope, see sky. So there's a lot of particle physics challenges for them. It's the same, the signature is quite the same. Actually, we have a few tricks up our sleeves to distinguish them, but it's exactly the same.
I'm realizing the YouTube people can't hear the questions, so.
Oh, yeah, I will repeat your question. I know. Yeah. Yes. Yes. Yeah.
And there are different parts of the world.
Yeah.
Where they're looking at different parts.
Excellent question. Definitely an astronomer question. So something else I didn't tell you is that the neutrinos can travel through the Earth. So even though we're at the South Pole, we can see the sky below our feet. So we actually look at the whole sky. And in fact, in some parts, in some analyses, it's better to look through the Earth because some of those background particles I was telling you about that trigger our detector 3,000 times a second get filtered by the Earth. So it's true that our what we call sensitivity to declination is different at different declinations. But I forgot to repeat the question. So sorry.
The question was, the location.
Does the location of the detector matter? It must matter, was the question. Yes, it does, but not in the intuitive way you think. Because we can see what we call 4 pi, the whole solid angle, or the whole sky. And depending on what you want to see and how, it is sometimes more advantageous to look through the Earth. So it is complementary. So if you have a northern sky telescope and northern hemisphere telescope and a South Pole telescope, they are complementary, but not in the very instinctive way you think. But yes, is the answer. Absolutely, yeah. So as a detector, yes, you are so good, and this is why you're president. The question is, isn't it still good to validate if you had multiple detectors? And my answer is absolutely yes. Yes, we would love more neutrino telescopes around the world that at the sensitivity that is around the same. This has been such a, as you can imagine, our South Pole telescope has like 300 scientists from all over the world. The Mediterranean telescope has like 300 scientists from all over Europe. I don't know if you've ever been to a room with 600 scientists, but nothing gets decided. So it's a lot of coordinating effort, right? And we don't have one agency like NASA, right? So it's a little bit of goodwill, and we have to do the planning ourselves. This is something I'm really passionate about because we are at the generational turnaround of new detectors, and these detectors take like 10 years to plan and operate for 20 years, right? So as somebody who is, looking at another 20, 30 years in her career in this field, this detector, the next generation detector, is really important for me. And this is something I'm very passionate about, is like, I travel a lot to talk to people to try to coordinate these things, because like you said, validation, cross-validation, cross-referencing, complementarity, these are all keys in the next generation detectors. Yeah, absolutely. I'll go here, 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 and then I'll come back there. Yes. Yeah. Yeah.
Repeat.
Yes. Yes, so now that we have a neutrino map of our galaxy, what does it tell us? Excellent question. I always say in professional talks, when I give seminars and colloquia, that it brought up more questions than answers, and as often discoveries do. So even if you look at this map, right? Some obvious dots are missing in the neutrino map, and some seem to be a little bit, maybe possibly shifted. And I won't name anything because I'm not supposed to, but you can do that by eye and say, huh, that what is the same and what is different, right? And if you show these to, like, for example, gamma ray astronomers, their response is like, just let me study this map for like 20 minutes. I'll talk to you in 20 minutes, right? And they go on. And so the questions it raises is, how come we see some things that are similar and some are different? What does that mean, right? Particularly because as the energies go, this is stacked in the energy order. So radio waves are tracing low energy events in our galaxy. Gamma ray is high energy events in our galaxy. These neutrinos are energy comparable to about 1,000 times the gamma ray energy. So this is also not only the first nut-like map of our galaxy, but the highest energy map of our galaxy. These energies are not accessible with gamma rays for various particle physics reasons. So again, particle physics, very important here. So what does that mean? That means that this is not only a new messenger, a new particle, but it's also a new energy regime. So then the question is, does it have to do with the particle or the energy that some things are the same and some things are different? You can go more and more from there, but that's the kind of questions that we can ask for the first time, because we have access to a new particle and a new energy regime to observe our galaxy. Hope that makes sense as an answer. I kind of punted, I know. I realized this. We were gonna come here, yes.
So I have a question from YouTube.
YouTube question.
From Jeff Kaler. Can
Hi,
you comment on the Zooniverse citizen science volunteers that are used by IceCube?
Thank you, yes. My colleague at Drexel, Christina Love, so Professor Christina Love, who we work together. She's part of the IceCube group. She started this Zooniverse project. So this is citizen science. You can go online, zooniverse.org, I think it is, and you can look for IceCube or neutrino or whatever it is, and you can help us sort the particles we see in our detector. So that I was telling you, we have 3,000 particles per second that we see. We need to sort this. We have over 10 years of data live, like every second of the last 10 years, and 3,000 per second, and you can do that calculation. And we have ways to automatically sort them, but these sorting systems fail quite often. And so the new idea is to use some machine learning, some artificial intelligence to do it better. And Christy and I had this idea of what about we just ask the people? How does it compare to artificial intelligence? So we asked the volunteers, and you could be one too, to sort them and tell us what kind of particle we saw, essentially. And we compare the results to the artificial intelligence version. And we are trying to learn something about learning about our data. And we're also trying to spread the word about IceCube. So thank you for that question. This would have been the right place to talk about Zooniverse. And I'm really thankful that Jeff, you asked that. Thank you.
Well, everyone, we have a raffle prize back there. It's a book on the Zooniverse.
There is a raffle prize back there that is a book on the Zooniverse project that you should definitely get if you win the raffle. Okay, I have more questions, right? Yes.
So neutrinos are going through Earth.
Yeah.
So and also means they're going through our bodies.
Yes.
Yes. So
Yeah, uncomfortable too.
so as they're going through
Yes.
everything, are they in any way taking anything with them? If you know what I mean?
Yeah, I feel like Dan Brown would enjoy this question much more than. This question is, as neutrinos, since they're everywhere and they're going through everything, they're going through our body, is it taking anything away from us? Yes, our despair and suffering, so obviously. No, so I think the honest answer is because they're not electromagnetically charged, and again, sorry, we're back in particle physics land. They are neutral particles, unlike the electron, which is negatively charged. Neutrinos are, as the name implies in Italian, neutral, neutrino, little neutral thing. So because there's no long range interaction mechanism in particle physics of neutral particles like neutrinos, and they only interact weakly, as we were saying, again, weakly interacting is a technical jargon. So unless they really hit and break the nucleus and really cause a particle, spray a particle shower, which is the kind that ice cube detects, they really don't do anything. They just go through us completely unaffecting anything until they actually interact. So it's either all or nothing. They do nothing, or very, very, very once in a while they interact, and a lot of things happen that we can see in ice cube. Yeah. Yes.
So do you have more topics you wanted to cover?
No, this was it. This was the conclusion. So I'm happy to go as long as you guys want. I'm also happy to let you two gauge when we need to release people back to their homes. That is both okay with me, but okay, I can definitely take more. Does ice cube detect supernova neutrinos? So yes and no, they are not in our sweet spot. We are way too high energy for supernova neutrinos. We do have a dedicated system that we run to check. So in our detector kind of, how can I explain this? The way we see supernovae is not in that particles and then triggering, and then we see particle, but the whole underlying noise level goes up. This is the only way we can detect it. So this is a completely different detection mechanism, and it's not a good one, I have to say, because it's not built for these energies, but we do try. So that's a really good question. Yeah. Oh, yes.
Most familiar with neutrinos. Beta decay.
Yes.
Those are not monitored.
Yes, absolutely.
Beta
Yes. Yes.
get a range that's
Mhm.
connected.
Mhm.
What I don't know is nuclear fusion, like
Yeah.
stars.
Yeah.
Is that a mono energy neutrino? Because I know it's not anti-neutrino,
Yeah.
it's neutrinos, but are they of the single energy?
No, so I put I swept a lot of technical details under the rug that you guys are forcing to pull out. This is one of them. So, I did say neutrinos, are created in nuclear fusion and fission, which is not untrue at all. But probably what we're detecting at Ice Cube is not, what we're detecting at Ice Cube, we think, is the black holes, the supermassive black holes, or the extremely energetic stars. What they're doing is they're actually accelerating charged particles, because we think it's a magnetic field acceleration that it's so high energy that we don't know of any nuclear processes that can reach these energies for neutrinos. So we think what's happening is there's a magnetic field acceleration of charged particles. These things, because when you excite a lot of things together, they interact. And in that interaction, we think that the neutrinos are born. So if you think about like a blazar, and again, tread carefully, particle physicists pretending to know what a blazar is. So these are like a supermassive black hole, very energetic, and that they have a beam of a particle beam pointing at Earth. That's what a blazar is, I've been told by my astronomy colleagues down the hall. So in that jet, which is a particle jet, which is very energetic, there must be some interactions. There has to be. Actually, I think there cannot not be interactions that produce neutrinos, for example. So it is actually kind of a marker of any time there is extremely high energy electromagnetic acceleration. And that's what we're actually tracing. Kind of lied about that. Yes. Yes.
Any idea of how large these particles are?
Yeah, so how do I answer this? I told you neutrinos have mass. And so mass is a fundamental thing in particle physics, whether you're massless or not. If you know what the Higgs boson is, or if you heard of the Higgs discovery, this is kind of related in all this. Anyway, so it's a big deal in particle physics. So we know that the neutrino is not massless. This isn't how, my sentences have a lot of double negatives, but this is how the field operates. We don't know what the mass of the neutrino is. That is an ongoing study. There's like, I think 15 different experiments around the world trying to figure that out. It is really hard because it is very small. So we know it's very small. For our purposes in IceCube, because we deal with such high energy neutrinos that possibly could come from actually fusion and fission, but actually are more likely from magnetic acceleration of other particles. The kinetic energy of the neutrino is so large that the very minuscule amount of mass on top of that does not matter. For all intents and purposes, we can think of it as massless. So I'm probably not the right person to answer that question. I'm actually half of these questions I'm not the right person to answer, to be honest with you. But this is such an active field that's close to me that I don't want to do a disservice to the people who actually spend their lives figuring out what the mass of the neutrino is. Yeah, for us, it could be zero. That's okay, because they're so high energy, they smash into an ice molecule, they break the nucleus, right? I mean, this is like energy higher than what the Large Hadron Collider, the LHC at CERN produces. So for us, the additional intrinsic mass on top of that does not matter. Sorry, that's a cop out.
Considered a point.
Yeah, absolutely, yeah.
Wow, that was amazing. Thank you so much. All the energy that you brought has been reflected back from the audience. That was a fantastic talk. Thank you so much. And I hope you come back when you have more data.
Oh, yeah, I want to do the rooftop, the telescope rooftop. We want to buy a telescope.
Okay. Okay. Well, I guess it's auction time. I mean, raffle time, sorry. I guess it's time to shut down the YouTube. Goodbye, everybody on YouTube. Thanks for sticking with us.